Hello students. In today's class, let us derive the relation among various quantities associated with reflection of light through mirrors. So first, let us derive the relation between the radius of curvature r and the focal length of the given mirror. So remember students, in deriving these relations, following assumptions are made. So first assumption here says that the aperture of the mirror is considered to be very small in comparison with the radius of curvature of the mirror. Second assumption says that we consider only paraxial rays. Only paraxial rays are considered. So what are these paraxial rays? Paraxial rays are those rays of light which are incident very close to the principal axis. Let us imagine that we have a concave mirror. So this will be the principal axis of the mirror. Let us consider we have a ray of light which is incident close to the principal axis, such that the angle of incidence and angle of reflection becomes very small. So what exactly is this? So first, let us understand the condition under which we consider the ray of light to be a paraxial ray. So let theta be the angle of incidence. Then, so if theta is the angle of incidence, then if the conditions like sin theta becomes equal to theta and tan theta becomes equal to theta, then we consider the ray of light to be a paraxial ray. So, and remember, this condition will be valid only in radian measure. So what exactly is this? Let us realize this with a simple example. Suppose if we consider theta to be equal to 6 degrees. That means we have a ray of light which is incident at an angle of 6 degrees on the given mirror. So if you find out the value of 6 degree in radian measure, so to convert degrees to radian, so we multiply with pi and divide it by 180. That is 6 into 3.14 divided by 180, which comes out to be equal to around 0.1047 radian. Same way, using your Clark's table, if you find the value of sin 6 degrees, sin 6 degrees will come out to be around 0.1045. Similarly, if you find out tan 6 degrees, it comes out to be equal to around 0.1051. So now you can see that if you take the value of sin theta, so sin 6 degrees will be equal to 0.1045, which is equal to 1.1047 radian. Same way, tan 6 degrees will be equal to 1051, which is almost equal to 0.1047 radian. So whenever this condition is satisfied, we can consider the ray of light to be a paraxial ray. So if you proceed in the same way, you can see that up to around the angle of incidence to be less than or equal to 10 degrees, you can see that this following conditions will be satisfied. So as a result, any ray of light incident at an angle less than or equal to 10 degrees can be considered as a paraxial ray. Can be considered as a paraxial ray. So with this as a assumptions, let us first try to derive the relation between the radius of curvature and focal length of a given mirror. So in order to find out this relation, either we can make use of a convex mirror or you can make use of a concave mirror, and you can prove the relation between the two comes out to be the same. So let us imagine we have a concave mirror. So we have a concave mirror with C being its center of curvature. Let us mark its pole, focus. So let C be the center of curvature, F be its focus, and P be its pole, and PA is the principal axis of the given mirror, such that the distance of the center of curvature from the mirror or from the pole of the mirror, that is the distance PC, will be the radius of curvature of the given mirror. Similarly, the distance of the focus from the mirror, that is the distance FP, will be the focal length of the given mirror. So let us consider we have a paraxial ray. So remember, here we have a paraxial ray which is incident on the mirror, but just for understanding we are just putting the ray of light to be at a considerable distance. So remember, we are considering a paraxial ray, a ray close to the principal axis. So let us consider you have a ray of light MN incident at the point N on the mirror. So let us measure the angle of incidence. So angle of incidence is measured from normal to the incident ray. So normal drawn is the line passing through the center of curvature and point of incidence. So let us consider this angle to be equal to theta. Theta is the angle of incidence. So same way, just by measuring the that is by using the laws of reflection, you can trace the reflected ray and consider the corresponding the reflected ray of light, the path along which the reflected ray travel. Now here, so you can say that the angle NCP will be equal to theta, as they are alternate angles. So using the laws of reflection, you can see that the ray of light after reflection passes through the focus. So this will be your reflected ray, making an angle of reflection equal to the angle of incidence. So same way, just by using geometry, you can say that the angle NFP will be equal to 2 times theta. Again, they are alternate angle. Angle MNF and NFP are alternate angles. As I said, they are equal. Now, so let us draw a perpendicular from the point N to the principal axis such that it meets at the point D. So now, using this, let's try to derive the relation among these two quantities. So to start with, let us consider the triangle like CND. So in triangle CND, we can write the value of tan theta to be equal to ND by CD. Similarly, if you consider your triangle like FND, we can write tan 2 theta to be equal to ND by FD. So let us call these equations as equation 1 and equation 2. Now you can see that. So here we are considering the paraxial rays. Since the paraxial rays are considered, so you can say that, so this will be your point of incidence, something like N. So if you drop a perpendicular from N to the principal axis, you can see that the point where the perpendicular meets the principal axis will be almost at the point of incidence itself. So if you consider a paraxial ray and if you drop a perpendicular from the point of incidence to the principal axis, the point where it meets will be very close to the pole of the mirror. So as a result, we can say that as the paraxial rays are considered, point D is very close to point P, that is the pole of the mirror. So as a result, we can write the distance CD to be almost equal to CP, which is nothing but the radius of curvature of the given mirror. Similarly, the distance like FD can be written to be equal to FP, which will be equal to the focal length of the given mirror. Similarly, we have seen if a paraxial ray is considered, tan theta will be almost equal to theta and tan 2 theta will be equal to 2 theta. So thereby, by using these conditions, you can rewrite your equation 1. So equation 1 becomes tan theta becomes equal to theta, which will be equal to ND by CD is equal to CP, which is equal to R. Same way, you can rewrite your equation 2 using these conditions such that 2 theta becomes equal to ND divided by FD, which will be equal to FP, which is nothing but the focal length of the given mirror. So let us call these equations as equation 3 and 4. Now you try to relate the two or substitute the value of theta in one equation or divide one equation with the other. So whichever way it is convenient. So let us substitute equation 3 in 4 for the value of theta. Therefore, equation 4 becomes 2 times ND by R, which will be equal to, that is I am writing for theta, which will be equal to ND by F. So ND gets cancelled. So I will be left with 2 by R to be equal to 1 over F, or you can write R to be equal to 2 times F. R will be equal to 2 times F. Or you can also write that F to be equal to R by 2. So as a result, the focal length of the given mirror will be always equal to half its radius of curvature, or radius of curvature will be equal to 2 times its focal length. So that's why whenever we mark the focus should be at the midpoint of the line joining the center of curvature and its pole. Next, here let us apply the sign conventions. So using sign convention, so you can see that we require the sign convention for F and R. So F here will be, so in this case the incident ray will be in this direction. If you measure, this first sign convention says that all the distances are measured from pole along the principal axis. So if you measure it from pole to the focus, which is nothing but the focal length, so you can see that they are opposite to one another. As a result, focal length will be negative. Similarly, if you measure the radius of curvature, which is the distance measured from pole to the center of curvature, this will be your radius of curvature. Again, they are opposite, that is radius of curvature is measured opposite to the direction of incident light. As a result, radius of curvature will be negative. So if you substitute these two in the following relation, you can show that again R becomes equal to 2 times F. So this will be the relation between the radius of curvature and focal length of a given mirror that you are going to make use. So keep in mind, student, this is one of the important relation, one of the important question for your exams. They may ask you to just mention the relation along with the explanation of the terms, or they may ask you to derive the same by making use of the following method. You can arrive at the relation between the two. So the same relation can also be proved by using a convex mirror. So in your exams, either you can choose a concave mirror and arrive at the required relation, or you can make use of a convex mirror and you can see that you will arrive at the same relation. Next, in your exams, you need not show the proof of this particular part. This is just for your understanding. You can just start with the assumptions, go for the ray diagram with a simple or a brief description, then proceed with the required relations. So this part is just for your understanding. So from here to here is just for your understanding. That is, we try to realize the condition under which a ray of light is considered to be paraxial, and we proceed with the required values. Next, on the same lines, let us derive the relation between the object distance, image distance, and the focal length of the given mirror, which is referred as mirror formula. So mirror formula gives the relation between object distance, image distance, and focal length of a given mirror. And again, this is one of the important questions for your exams, which will be asked for 5 marks. So again here, in deriving this relation, we go for the same assumptions. So first assumption says that the aperture of the given mirror is very small in comparison with its radius of curvature. Second assumption is, again, we consider only paraxial rays, that is the rays which are very close to the principal axis, so that the angle of incidence will be equal to angle of reflection, which becomes very small. Now using this, let's try to arrive at the relation between u, v and f. So as I have told you in the previous discussion, that whenever we need to derive the relation between these quantities, we can consider any one of the cases. That is, we see, depending on the position of the object and size of the mirror, both the position and nature of the image also changes. So you can consider any one of the following cases, any one of the different cases, or you can consider convex mirror and you can arrive at the required result. So let us consider here, you are given with a concave mirror. So we have a concave mirror with C being its center of curvature, and try to mark the center of curvature will be somewhere here. Center of curvature, mark its pole, focus, and draw the principal axis. So C being its center of curvature, F being its focus, P being its pole, and PA being its principal axis. Now, to arrive at the relation between these quantities, let us consider we have an extended body. We have an extended body, say AB. So AB here is the object such that we shall consider the distance at which the object is placed from the mirror or from the pole of the mirror, which is referred as the object distance. So here BP gives the object distance, which we represent it as u. Similarly, to find the position of the image, the method followed is, we consider, say, a ray of light which is parallel to the principal axis. let it be incident on the mirror at some point, say M. So remember, here we consider a paraxial ray. That means to say the point M, the ray of light is very close to the principal axis. So that point M will also be very close to the principal axis. So after reflection, the ray of light, the reflected ray of light, will pass through the focus of the given mirror. Will pass through the focus of the given mirror. So same way, to measure, that is, to get the position of the image, we consider the another ray of light. Let us imagine here the second ray of light we are considering here is the ray of light which passes through its center of curvature. So you have a ray of light passing through its center of curvature, such that a ray of light incident along the center of curvature will retrace its path, as that becomes the normal incidence. And the point where the reflected rays meets will give you the position of the image, say like A dash, corresponding to a point A on the object. Same way, to get the position of the image corresponding to a point B on the object, the method followed is we drop a perpendicular from A dash to the principal axis. The point where the perpendicular dropped meets the principal axis will give you the image, say B dash, corresponding to a point B on the object. So A dash, B dash here gives the image of the object, and the distance at which the image is formed, that is B dash P, will be the image distance. Image distance V. Same way, the distance of the center of curvature from the pole of the mirror is its radius of curvature. So here the distance CP will be the radius of curvature. Radius of curvature represented as R. Same way, the distance of the focus from the mirror is nothing but its focal length. So FP will give you the focal length of the given mirror. So FP will be the focal length of the given mirror. Now, using this, let's try to arrive at the relation between these quantities, for which in this case just we will drop a perpendicular from M to the principal axis, such that it meets the principal axis, say at some point D. So that as we are considering the paraxial rays, point D will be very close to point P. Now, so using your geometry, we can say that your triangles like A dash, B dash, F and the triangle MDF will be similar triangles. So triangles A dash, B dash, F and MDF are similar triangles. And using the properties of similar triangles, we can write that the ratio A dash B dash to MD will be equal to the ratio like B dash F to FD. So in this case, you can see that the value MD will be equal to the AB, which is the size of the object. So MD will be equal to AB, and as we are considering the paraxial rays, point D will be very close to P. Therefore, you can say that FD will be equal to FP and FD will be equal to FP. So you can write, since D is very close to the point P. Same way, by using these values, you can write that a dash b dash to md will be equal to ab, which will be equal to b dash f to the value fd, which can be rewritten as fp. Let us call this as equation number 1. Same way, if you consider your triangles like ABC and A dash B dash C, they are similar triangles. Triangles A dash B dash C and ABC are similar triangles. Again, by using the properties of the similar triangles, you can write the ratio of A dash B dash to AB, which will be equal to B dash C to BC, that you are going to get it. So now, let us call this as equation number 2. So on comparing these two equations, like equation 1 and 2, you can see that the left hand side are one and the same. So as the left hand side are one and the same, the right hand sides will also be equal. Therefore, you can say comparing equation 1 and 2, we get b dash f to fp will be equal to b dash c to bc. Now our work is just to rewrite these values in terms of your object distance, image distance, radius of curvature and focal length. So let us see how exactly we write it. B dash f, the value of b dash f can be written to be equal to b dash p minus fp. So b dash f can be written as b dash p minus fp, whereas fp is the focal length, so you can write as it is. Same way, try to rewrite your value like b dash c. B dash c can be written to be equal to pc minus b dash p. B dash c can be written as cp minus b dash p, and bc can be written as bp minus cp. bp minus cp. Now on rewriting these values, so you can see here b dash p is nothing but your image distance v, fp is nothing but your focal length f, again fp is nothing but the focal length f, which will be equal to pc is nothing but the radius of curvature, pc is nothing but the radius of curvature, b dash p is nothing but your image distance, b dash p is your image distance, bp is the object distance, and cp or pc is nothing but your radius of curvature. So now we need to just modify this relation, rearrange this relation so that we get the relation between the required quantities. So let us see how exactly we do this. So let us cross multiply this equation. So on cross multiplying, the first term you are going to get here will be vu, second term will be minus vr, next you will get as minus uf, minus of minus plus fr. This will be equal to, right hand side you will get it as fr minus fv. So just rewrite this. We can rewrite it as vu minus, since r is equal to 2f, you can write this as v into 2f, that will be 2 times vf minus uf. Again you have r to be equal to 2f, so 2f into f, it will be 2f square. Take it on to the other side, again r is equal to 2f, it will be 2f square plus fv, which will be equal to 0. Now you can observe here that, so you have plus 2f square and minus 2f square. So you have VU, written it as it is, minus 2VF, and VF plus VF will give you minus VF. You will be left with minus UF, which will be equal to 0. So on simplifying these two terms, minus 2FV and plus FV will give you minus FV. Now divide this equation throughout by UVF. So on dividing throughout by UVF, the first term, okay, we can rewrite one more step. So you have UVF minus VF by UVF minus UF by UVF equal to 0. So in this first term, we are left with 1 over F. Second term, we are left with VF will be cancelled, so we will be left with 1 over U. In the last term, you are left with UF, so it will be 1 over V, which will be equal to 0. So on rewriting this relation, you can write 1 over F to be equal to 1 over U plus 1 over V. So this will give you the relation between the focal length F, object distance U, and image distance V for the reflection of light through the concave spherical mirror when the object is placed beyond a point C. And as we have seen, as and when the position of the object is varied, both the position and nature of the image changes. So you need to repeatedly make use of this relation. So in order to avoid that, in order to overcome such difficulties, we make use of sign convention. So here, why we are using sign convention is, we have to convert the given equation that holds good for a given situation into a generalized relation. So if we make use of sign conventions, we need to apply the sign convention for these three quantities, namely F, U, and V. So first, coming on to F. So here you can see that the incident ray is from your left to right like this. So if you measure, the first sign convention says that the distance are measured from pole along the principal axis. So we require the focal length. So focal length is the distance measured from P to F, which is opposite to the direction of incident light. So as a result, by convention, focal length becomes negative. Similarly, coming on to your object distance. So object distance is the distance of the object measured from pole. So from pole to the object is your object distance. Again, the object distance is measured opposite to the direction of incident light. So by convention, it becomes negative. So similarly, your image distance, which is the distance of the image measured from pole. So this will be your image distance, again measured opposite to the direction of incident light. So V becomes negative here. So on substituting these values, you can again see that 1 over F, which is negative here, object distance is negative, and image distance is negative. So on simplifying, you will arrive at the relation like 1 over F to be equal to 1 over U plus 1 over V. So this is referred as your mirror formula or mirror equation. So remember, this is a generalized equation, and using this generalized equation and applying the proper sign convention, we can convert the given equation, we can modify the given equation so that it holds good for any of the situation, that is irrespective of which type of mirror is used and what is the position of the object. So use this equation, modify the equation by using the sign convention, proper sign conventions, so you can get the relation between U, V, and F for any of the given situations. So practice these two derivations properly. Both are very important as far as your exams are considered. So how we exactly make use of the sign convention and how we convert a generalized equation so that it holds good for any of the given situations. So we will learn that in the next part. Once we go for discussing the numericals, it becomes more and more clear. So today we shall stop here. In the next class we shall go for one more such derivation, and then on we shall practice by using some numericals how exactly we make use of these relations and the sign conventions so that we arrive at any of the required results. Thank you, students.